Welcome to the very short and sweet video key for the first chapter 5 homework. First problem we got here is number 42, A, B, C, and G. This one asks us to label or find how many chiral centers there are, and we'll label them as well. So remember, for a chiral carbon, chiral center, we're looking for a tetrahedral, an sp3 carbon, that's attached to 4 unique things. So this carbon is attached to 3 H's and another carbon. Okay, so that's not 4 unique things. This one's attached to a carbon, a different carbon, right? This is a different type of carbon. This is not a CH3 like this one was. So it's attached to a CH3, another type of carbon, an OH, and then there's also that H that's not shown. So this would be a chiral center. Same thing with this one, okay? 1, 2, 3, and then the H would be a fourth different group. These two are different groups because they're not exactly the same, right? This one we have a carbon which is attached to an OH and a CH3. Here we have a carbon attached to an OH and attached to another carbon that's attached to an OH. So these two are not equivalent carbons. So this one is attached to 4 unique things. Okay, same thing with this one, and same thing with this one. So I have 4 stereocenters or 4 chiral centers in this molecule. B, okay, if I check each carbon, my carbons on the end, none of these are going to be chiral because they're all CH3s. Then looking at this one, it's connected to 2 identical CH3 groups. So this one's not chiral, this one's not chiral. If I look at this one, I'm attached to like an isopropyl group on this side, a methyl group on this side, and then a longer sort of group on the right side, right? This is not just an isopropyl anymore. So this one's attached to 4 different groups, and its neighbor is the same way. Okay, if you count through, it's attached to an isopropyl, a methyl, a bigger carbon chain, and an H, so that one's also chiral. So this one has 2 chiral centers. Okay, on C, remember, I have to only look at sp3 carbons. That rules out this entire benzene ring because these are sp2s all the way around. So none of these carbons on the benzene rings are ever going to be chiral. That just means I have to look at these chain carbons at the bottom. So this is a CH3. That's definitely not 4 unique groups attached. This one also has 2 H's, right? And this one has 2 H's as well. So none of these carbons are chiral. So this has none, no chiral carbons. And then G, this is the trickiest one, I would argue, or a tricky one anyway. Okay, we can eliminate these as choices because these all have 2 H's, right? This is a CH2, this is a CH2, CH2, and a CH2. So none of those ring carbons could be chiral. This one looks like it would be chiral at first glance, but because of the symmetry of this molecule, this side, this carbon it's attached to, is equivalent to this carbon that it's attached to. Okay, because they're both like 2 carbons away from this chlorine, 2 carbons away from the chlorine. Okay, so because these 2 carbons, this is a symmetrical molecule, or we have a plane of symmetry right down the center, neither of those carbons are going to be chiral. This one's not chiral, and this one's also not chiral, because then these carbon and this carbon are equivalent to each other. So this one also has none. Okay, 71 I'm going to actually bring my book under the cam for, so let me pause while I do that. Or hang on, let me give you like a classic YouTube editing thing, okay? I'm going to touch this with my pencil and it's going to turn into the book. You ready? Boom. Okay, movie magic. We created the book. Okay, so 71, we're doing all parts of 71. And we're trying to figure out, are these enantiomers, diastereomers, constitutional isomers, the same molecule, conformers, or none of the above? They're different molecules. Okay, so with this first one, these both have 6 carbons if I count it out, but this one has a ring, which would be, a site of unsaturation or 1 degree of unsaturation. This one is fully saturated. So my molecular formulas, we know from NMR when we have a site of unsaturation that that's going to change what our molecular formula is. It's going to change the number of hydrogens. So these are not related. Okay, these are unrelated. They're different molecules. Here, okay, remember a ring, as far as unsaturation goes, a ring is equivalent to a double bond. So on this one, okay, I have 1 ring on this structure and 1 double bond on this structure, so their molecular formulas should work out to be the same. So these would be constitutional, right? Their connectivity is definitely different because I have a ring here, whereas I don't have a ring here. This one, again, thinking about unsaturation, this has 4 degrees of unsaturation. The ring itself plus 3 double bonds. This one only has 1, so these are also unrelated. These have different molecular formulas. They're not isomers. D, I saw a lot of people, well, so I kind of graded this one based off of what was in the solutions manual. So shame on me for that. But if you look at the solutions manual actually didn't draw this molecule correctly. They chopped off a carbon. So if we count, and this is probably a misprint in this part of the text, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons on this side. 1, 2, 3, 4, 5, 6, 7, only 8 carbons in this molecule, so they're not isomers. They would be unrelated. Okay. The book says, or the solutions manual says D, they're constitutional, but they can't be constitutional isomers if they don't have the same molecular formula. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9 versus 1, 2, 3, 4, 5, 6, 7, 8 carbons on the right one. Okay, E, see if I can get my camera to focus a little better here. E, we have a chiral nitrogen, an sp3 nitrogen, okay, that does not have a lone pair on it, so it is chiral. It does not undergo that inversion, okay. So if I look on this one, I have the methyl coming out of the page, and this one I have the methyl going into the page. So that's going to change my conformation at that nitrogen. Basically, what I've done is invert this stereocenter, inverted this chiral nitrogen, and changed its configuration. So one of these would be R, one of these would be S, and these are enantiomers. Then they're the mirror images of each other. Okay, F, we start getting to things that are a little bit harder to see. So I'll just compare. These are both. Each carbon is chiral. Okay, so I want to see, did my configuration of any of my chiral carbons change? That's the first thing I'm going to look for. This carbon looks exactly the same as this carbon, right? They both have the H in the plane, the CH3 back, and the Cl coming forward. So these chiral centers are the same. And this one, it looks like they're different, but really all I did was rotate this. So I rotated this bromine into the back, which is going to pop this CH3. Wait, did I rotate the bromine into the back? No, I rotated the other way. So I rotated this, what's the easiest way to say this? I rotated this H all the way into the back, so it took the place where the CH3 was. And then the bromine is going to slide down into the plane where the hydrogen was, and that's going to cause the CH3 to kind of pop out of the page now. So if you build this as a model and you actually rotate this bond to where you get the bromine in the plane, you'll see the CH3 and the H are in the correct place. Okay, other thing you could do is actually assign R versus S to these now that we know how to do this. And you'll see that the stereochemistry did not change. The chiral center is still the same configuration in both of these. All we did was rotate that bond. So those would be conformers, right? Conformers is when we rotate the molecule about a single bond. Okay, question G. If I look at my chiral carbons, so I've flipped this molecule is flipped around compared to this one. So this carbon is this carbon on this side. And you can imagine if I drew a mirror right here that this looks like the mirror image of this molecule, right? Bromine is the mirror image. Methyls are the mirror image. Same thing over here. This CH3 is the mirror image of this one. This Cl is the mirror image over here. If I were to redraw this in the same orientation, I would have to flip this molecule around 180 degrees. And that would then show the bromine going into the page and the CH3 coming out of the page, which is the opposite configuration of what I have at this carbon. Okay, same thing here. This, if I flip this molecule over 180 degrees, I would have the Cl going into the page and the CH3 coming out, which is the opposite of what I have here. So since I inverted all my stereocenters, those two must be enantiomers. Remember, if you invert every stereocenter on a molecule, that's how you get its enantiomer. If you invert some but not all, that's how you get a diastereomer, which is what's happened on this one. Okay. So looking at this again, it kind of, well, this one's a little tricky, I guess, to try to visualize, right? If I think about this as a mirror plane between these two, if I try to draw the mirror image of this, then on this carbon, this chlorine would have to still be out of the page, right? But over here, I see it going into the page, and my CH3 is coming out of the page. So this carbon, this outside carbon with the chlorines on it, had its configuration inverted. If I look at this carbon, okay, again, if I rotate, I can rotate this H down to be in the page, okay, in the plane of the paper, so the H would rotate down. This CH3 would take its place, it'd be going back, and this bromine would move up to where the CH3 was, so the bromine would be coming out. So this carbon Okay, so this carbon actually did get inverted. Okay, this one, I may have misspoken a minute ago. This one did not get inverted. This is actually the same configuration that I started with. If you flip this 180, you'll see this chlorine would be coming out of the page and the methyl would be going into the page, right? This is not the mirror image of this side. These two are the mirror images of each other. So this carbon got its stereochemistry, its chiral center inverted. This chlorine carbon did not get its stereocenter inverted. Okay, so these are diastereomers because we only inverted one stereo center. Okay, this chlorine one did not invert. Okay, the last one is number 75. So let me flip the page. Okay, number 75 wants to know which H's would I need to substitute. Okay, substitute one H at a time to generate two new molecules. Which two H's could I substitute to generate a constitutional isomer? Okay, imagine if I'm swapping a chlorine in. Well, if I put a chlorine here, that's going to be a very different molecule than if I have a chlorine on any of these other carbons, right? Really, if I just pick any two of these carbons to swap an H out for a chlorine, that's going to give me constitutional isomers because constitution would be different depending on where this chlorine is connected. Okay, if it's on carbon 2 versus carbon 3, we're going to name it differently. That's going to be a new molecule. For enantiomers, I have to think about which carbon would become chiral if I put a chlorine on it. So this one would have, if I change one of these H's to a Cl, that would give it 4 new groups. This one up here, same thing. If I change this H to a Cl, we'd have 4 new groups. So my enantiomer would be, one enantiomer would have the Cl going this way. My other enantiomer would have the Cl coming out of the page because those would represent two different configurations of this carbon. I could also do that on this carbon. That could generate two enantiomers from this carbon. If I put a chlorine here, that would be one enantiomer. If I put a chlorine in my second molecule has the chlorine going back, that would be the other enantiomer. Okay, so this one or this one, if I swap the chlorine for hydrogen on the same carbon, but either going back or going forward, that would be my enantiomers. Then conformers, I need to put this on an achiral carbon so that when I spin that carbon, I can regenerate, any configuration or any conformation would be better to say. So if I substituted an H for a chlorine on this carbon, it wouldn't make that carbon chiral. So I could, if I substitute a chlorine like in this one, put it in the plane of the paper, I could just rotate this around to end up with the chlorine in any of these positions. So substituting a chlorine here is going to be the same molecule as if I substituted it here. Same thing if I substituted it here. It just depends on how we rotate this bond. And since it depends on rotation, those would be conformers. Okay, that's it for this homework. I'll see you on the next homework shortly.